Okay, so let's continue the PyTorch introduction. We saw the basics of PyTorch, the data structure and the fundamental operations like autograd and the backward gradient computations. Now let's look at how we can use PyTorch for deep learning, particularly for computer vision. Torch or PyTorch also has another library called Torch Vision, which has most of the computer vision related functionalities and libraries built into it. Um, so the one of the basic um, things to understand in PyTorch is how they handle the data sets. Um, so in For computer vision, so the Torch Vision has something called as data sets, and these uh, they already have some inbuilt data sets. This is what I am being loading here. So first I imported Torch Vision, and then from the Torch Vision, there's data sets. In the data sets, they have multiple data sets. And in this example, I'm importing the Cipher 10 dataset, which is basically a collection of images that are categorized into 10 categories. So I'm just telling where to import that data and then whether to import the training data, then what kind of transformation I have to apply to this data. So when we are downloading, it is downloaded as images. So what I'm saying is convert the NumPy array into PyTorch tensor. Okay, so that's what it is doing here. Now, once you created a data set, um, you also have to build a data loader on top of this data set. What is a data loader? Data loader is used for batching and parallel processing in the GPUs. Okay, so a data loader takes in a data set, which is in this case is a trained data set, which contains a lot of images that are categorized into these 10 categories. And then you say, hey, give me a batch of these data set, and the batch size would be 64. Now, when you do training, right? If you do a model training for, let's say, 10 epoch, and if you have about 100 images, and if your batch size is 60, let's say your data set size is 1000, and if your batch size is 64, which means that each epoch will have 1000 by 64 iterations, right? So for each iteration, it takes 64 images, do one forward pass and do one backward pass, and then again load the next 64 images, forward pass and backward pass, like that. It does that until it passes through all the images. That is one epoch. After that, then it goes to the second epoch, third epoch, like that. So then this is basically data iterator, which means that's what I explained now. It iterates through a batch size of 64 images. Then there are also some pre-trained models available within Torch Vision in the models module. So for example, here I am importing a pre-trained model called ResNet, which we will look into it later what this ResNet is. So what I'm saying is uh, create a ResNet model and also initiate that model with some pre-trained weights, which means this ResNet 18 model is already trained on some open source dataset like ImageNet, and those weights are preloaded into this model. Okay, which means we are initiating with some pre-trained weights. Now, in order to, I was telling, right, that if you want to freeze the layers, then you can set that request grad parameter to be false, which means that there will be no more gradient update for these layers. So in this example, what I'm saying is for every parameter in that pre-trained ResNet model, I set the request grad parameter to be false, which means that all the layers are frozen. Okay, so this is some precautionary step, or if you don't want to change the weights, this is what you need to do. Then what I'm saying is this pre-trained way model, right, which I downloaded from the internet, they are actually trained on a different set of classes. They're trained on some ImageNet classes, which has about 1,000 classes. But in our data set, as I already mentioned, it has only 10 classes. And this Cypher 10 data set classes are different from the ImageNet 1,000 classes. Although they look very similar, they are just internet images. The image names might be different. So what we are doing here is more of a transfer learning or fine tuning. We took the pre-trained weights from ImageNet and we are creating one more final layer. So instead of 1,000 classes, we create a new linear layer with 100 classes. I don't know why it is 100. Probably this data set has 100 classes of instead of 10. But let's assume that this is correct. And now instead of 1,000, the final layer will be 100. Now with this, I can go and then start a training, and then only the final layer, right, that will get updated. Remaining all things will stay the same. Okay. And then one last thing, like once you trained, you should obviously save that model so that you can reuse it later. The way to save the model in PyTorch is torch.save, and then use PTH format to save the models. This will save both the model architectures and the weights. Okay. Each not exactly same, so but sort of a binary format which encodes all the model architecture information and weights into it. But in machine learning, when you're saving the SVM model, I think you save it as pickle, right? In, but PyTorch, you don't save it as pickle, you save it as PTH. Yeah, that we will come to the transfer learning. So there is a quite a lot of similarity between Cypher dataset and ImageNet datasets. So what is the assumption is that a lot of the weights that are being trained using the ImageNet can be reused for Cypher 10. But in case if you are reusing this for a different domain, for example, some sort of an industrial inspection where the images looks completely different from the internet images, then you cannot freeze the layers and reuse it, then it will not work at all. You need to unfreeze those layers and then you need to train it so that those layers get adapted to the new domain that you're training in. If it's a very similar domain, you can freeze it. There's a certain guidelines and best practices for transfer learning. We will look into it, but this is again a very imaginary example I just put. Just I'm showing you how you can freeze the layers. Yeah, fine tuning. Yeah. For example, if you are doing for a completely different domain, um, let's say industrial domain or medical domain or something like that, you cannot train by freezing the layers. It will not work. Okay.
So after this, how can we use this PTH model?
By torch.load like this. For example, once you train the model, then you save the model. You can save it either by this way or by this way. Okay. Then there will be like a ResNet model.pth file in your file system. Then what you can do is you can say torch.load and then ResNet model.pth. Then this model will have all the model layers and the weights loaded. Then you can either use it this way. There is also sometimes this way of loading might create some problem. You follow me? Uh, so what they usually do is instead of saving, see there is two things, right? In model we have the layers, like what convolutional layer, what is the kernel size, what was all those things. And then we have the weights, which is learned. When you both save both things in one file, sometimes they do not load properly. So what is the typical recommended way is just store them the weights separately. Okay. Then you know that this model architecture, right? So this is what the architecture we used. We used a pre-trained ResNet and only in the final we added a linear layer. This ResNet doesn't have any weights in it. Then what I do is I just load the weights into that model. So this way is expected to work better and reliably and consistently than that old model. I mean, this way of saving and loading. Okay. But just for beginner, do not worry too much about this. This simple way of saving and loading should work. In case if it doesn't work, just try this.
So loaded model is instance of model.
Yeah. Loaded model is basically contains both the architecture and the weights loaded into one single line of code. So in this, you understand the difference between these two, right? This in one single line, I load both the architecture and the weights. In this first, I create the model without weights and then load the weights into it. Okay, so we just saw a quick introduction to PyTorch. Uh, Now let's see image classification using CNNs in PyTorch. In this, we will build and train a CNN model for image classification using PyTorch. We will use a dataset called Cipher10, which has 10 classes. So what we will go through is how to load a dataset, how to prepare a data loader, how to define a model, and how to train it. Okay. This also I will share. Then, okay. So here I'm importing Torch Vision, and there are some utility functions like download URL, then random split. So here is tar file which contains all the images. Then I'm extracting those images into local file system in a directory called data. That contains a subdirectory called cipher10 and which has a train and test folder. And in each of these folders, you will have 10 subfolders. Those are those 10 image classes: frog, dog, deer, horse, bird, airplane, automobiles, ship, truck, and cat. Okay, these are the 10 classes. So the task here is an image classification, very simple and straightforward. Given an image, we have to classify whether the image belongs to one of these 10 classes. Okay, so it's a multi-class classification problem. Okay. Let me see if I can run this. So in this, since we are training a proper deep learning model, I think it's better to initialize the collab with the GPU. So I'm going to change the runtime from CPU to GPU. Okay, then let me see if this works. Okay, it still works. Mhm. Okay, so now you can see, yeah. So there is a data folder created for me. Then there is an assignment 10. Within that, there is train and test. It's automatically splitted for me. So the train will contain again 10 classes. The test will again contains 10 classes. Okay. So what we will do is we will design an deep learning CNN network. We'll train that model using the train dataset and we'll test it on the test dataset. Have you done PyTorch in your previous courses or this is first step? First step. So all the deep learning, mostly you do it with Keras. Okay. So then, okay. Um, in Torch Vision, we first step in PyTorch is to create a data set and then build a data loader on top of that data set. Okay. So in order to create a data set, I'm using a function called image folder, which basically takes this path, which has a image folder data structure, which means that each folder is a class and it contains multiple example images of that class. The folder name is my class name. That's what this image folder assumes. Okay. And then it also, you can pass in the different image transformation that has to be applied to this data set. So in this, I'm just using a very basic converting into a PyTorch tensor. So what the help says is it converts a fill image or a NumPy array into a PyTorch tensor. Okay, that's what it does. But in some advanced training, what you can do, you can also pass in multiple data augmentation transforms like rotation, flipping, scaling, all those things, affine transformations, color transformations, all those things. You can configure it and then pass that transforms list into this transform. Okay, then it will apply those data augmentations into those images. Okay, so now this data set contains all the train images For example, it can take the first image and then display and show it to you. So if this is an aeroplane image and it shows you that the label is aeroplane and the class number is 0 and it is of the size 32 cross 32 with 3 channels. Okay. So just doing some EDA, right? Just looking at your data and see what type of images it has. Let me run this. Then you can just randomly visualize few images just to make sure that you understand the data set. Once you created a data set, right now we are splitting the train data set into train and validation data set. Okay, which means during the training, we will evaluate at the end of every epoch, we will evaluate it on the validation data set, and then we will display the model's performance progress on the validation data set. Okay, so the model weights will be updated on the train data set, but then we evaluate at the end of every epoch on the validation data set. So we have 50,000 train images. So we split them 45,000 used for training and 5,000 used for validation of every epoch. So this is understood, right? So now we have prepared the data set. Now we have to create a data loader. Now we define the batch size as 128. We say that, hey, we need two data loaders. One is the train data loader and val data loader. And this data loader is built on top of the train data set and the val data sets with a batch size of 128. And for validation, I'm using a batch size of 256. And you can also define whether you need to shuffle the data set or you just pick first to 64, next to 64 like that. Usually we do a shuffling so that there is no any unintentional bias in that. Okay. Um, then this is just basically some sort of an visualization, like how a batch of data looks like. Now we already built the train data loader. Now what we are taking is we are just taking one batch of 128 images and then visualizing. So one batch of image will looks like this. So now by looking at it, I see there is variety of images represented in each batch. So I'm good with it. But suppose let's say if one batches is completely one class dominated by one class, probably you are not doing shuffling or you're making some other mistakes and you need to fix that before starting training, right? So these are the small things you just have to take care before directly jump into training so you understand what is going on. So now comes the important part of building your neural network. Okay. So as I told you in the introduction, the neural networks are built using the module called NN, which stands for neural network. And some of the activation functions are actually available in this functional modules, like ReLU activation function, softmax function are all available in this functional modules. Okay. Now, so see, this is different from how you do it in TensorFlow Keras. TensorFlow, what you do is you create your data set and then you say sort of CNN dot train. Probably you define layers, but once you define the layers, you say model dot train, right? You define your layers, you probably define your loss function, and then you say model dot train, which takes in your CNN model, your loss, your data set, and then all the forward pass, backward pass, update of gradient, calculation of loss, everything is taken care for you in the Keras. But here you need to define that. Okay. So that's what we are going to do. A one training step is what will look like this. So it has 3 steps. First, get a batch of data. Then what you do is pass those batch of data into your model, get the output, then calculate the loss between the model output and your actual output. So in this case, it is called labels. Okay. So load the data, generate predictions, and calculate loss. This is one single training step. Okay. Same you do for validation as well, but in validation, you not only calculate loss, but you also calculate accuracy. So what you do, you load a batch of data, you pass that batch of data into your model, you calculate loss by comparing the model's predictions with the actuals. Then what you do is you also calculate accuracy, because at the end of every epoch, you need to report the accuracy as well, such as F1 score or precision or recall, all those things you need to know, so that you can monitor how your model training is progressing. Suppose you put some 300 epoch and your model accuracy gets stuck with 65, and for another 50 epoch it is 65. You can put early stop, but let's say if it is you're printing out, then you kind of have a visual monitoring of it. And then this is for every iteration. See, this step is nothing but every iteration for every batch of data. But we also have epoch. So epoch will have a multiple iterations based on your batch size and your data set size. For every end of epoch, we need to print the epoch accuracy and things. So that's why we are printing this, right? Validation accuracy and validation loss. So after the end of epoch, we are printing that. These are some functions to calculate accuracy. So here is where, so here so far we have just built the basic things, and here we are defining the layers. So this one again follows the same pattern. It does a convolutional layer followed by an activation layer, and then a convolution layer, activation layer, then one max spool. This is one block. Then the same thing I repeat another time, 3 times I'm repeating. Okay. So after repeating 3 times, it is similar to what we have seen here, right? We repeat this probably 2 times we are repeated here, but here I'm repeating 3 times. Finally, I'm doing a flattening, which means take those feature maps, flatten it into one single vector, and then pass it into multiple fully connected layers. So these fully connected layers are nothing but linear layers. But after every fully connected layer, we have an activation layer called reload, right? So these are my layers of my image classification model. Okay. Then what we do is we define the forward function, which means it takes this network, right? This is my network, and takes a batch of images as my input, is called XP, and then pass that to all these layers. That is my forward pass. Okay. No, we have so many layers. So each one is a layer, right? 1, 2, 3, like that. 3 into 3, 9, and then 10, probably 10, 11, 12, 12 layers are there. Okay, but 3 blocks. You understand, right? So this is my layers. So actually you can see, if you ignore the activation layer, probably you have so many layers. Yeah. So then once we define the training steps, validation steps, and then the neural network layers, uh, we also define some utility functions. So these are nothing but some utility functions, which means getting what is the device available. do I have a GPU or not? Then if I have a GPU or CPU, I need to move the data to that. Okay. So if it is a GPU, then I say move the data to a GPU. So then it will take care of that parallel processing. Okay, let me run this. Did I run this? No. Okay. So now if you see, I already started the collab with the GPU. So that's why my available device is queued up. And this is where I am defining my for loop, like the multiple epochs, like the model dot train, right, in Keras, does nothing but this fit function. Okay. So it defines an optimizer, and then I have so many epochs. I am just doing a for loop, and for every loop, I am putting the model in train mode. And for every batch of my train data, I am taking the model through the train step and then calculating the losses, doing backward propagation, and then updating the weights. Okay, so this one will be done for um, all the batches of data in the data set. Once this for loops completes, that basically is my one epoch. You see this, right? The outer for loop is epoch, the inner for loop is the iterations. At the end of every epoch, I evaluate my model and I print my model accuracy. And then I keep track of my results in the history variable. Finally, I'm returning my history variable that will have for every epoch my validation loss and my validation accuracy. That's it. So now I'm moving my model to GPU, and then initially I just evaluate my model, which means now the accuracy is just 9%, which is a randomly initialized model. Now I'm going to train my model for 10 epochs. So now I'm going to call the fit function. Now my training starts. You see, all of things are mostly defined by you, and you know each and every step that you're doing. This is little bit more research focused because the researchers, they want to know what they are doing. So they don't always call model.train. So they need the flexibility that they can do um, all those customization and changes they require, right? So that's why researchers prefer PyTorch. At the beginning also, I was using Keras, but once I kind of went into PyTorch, I didn't go back because no, I fixed 0.001. So this is like a hyperparameter. You can change and see how it is. So we can see some linear improvement in validation accuracy. It started from 45, 59, 66, 72, 73. So it looks like the training is going as expected. So while it is trying to complete, I just have some few more helper functions which plots accuracy, which plots the loss, and then finally it saves the model. And you can also load back the model. Yeah, that's all about the image classification using PyTorch. We just have probably 10 more minutes. There's just one last important topic I want to cover. which is called transfer learning. This is what you'll be mostly doing because there is not a major reason that you would start training a model from scratch unless it is absolutely necessary. Mostly you will be using some pre-trained weights, which is trained on ImageNet or a similar domain dataset. And then you do something called transfer learning or fine tuning it onto your custom dataset or a custom domain. Okay. So that's basically it's called transfer learning. So how do they do transfer learning, right? So let's assume that this is a CNN network that we want to use. So it has series of convolutional pooling, convolutional pooling, convolutional pooling, convolutional pooling. So it can be like 150 layers, 180 layers. And then finally we have fully connected layers. There can be 2 to 3 fully connected layers before the final classification layer. So usually what they do is they just remove the final fully connected layers. They just throw it away, right? And then you add a new fully connected layer because the pre-trained model will be used in a different number of classes. They would have trained in 1,000 classes, but now you are training it for a data set of 10 classes, right? So which means the final output in the original model will have 1,000 nodes, 1,000 classes. So now you just need to remove that and add a 10 node classification layer. And the final layers doesn't make sense anymore because they are completely different. It is used for 1,000 classes. But what makes most sense is whatever the initial learning that has been done. Because as I told you, right, the convolutional layer, they have different levels of learning. The first few layers, they learn the low level features like edges, curves, lines, and curve, other things. And then still slowly build these layers into the high level shapes and in order to recognize those objects. But these low level features are common for any domain, right? Any domain, we need edges information, we need curves information on all those things. So that's why the initial layers will be very useful and it can be reused for most of the domains. Okay. Only the final layers will not be relevant. It will be completely different. That's why we slice the final layer and add new layers and we train only the final layers. So what we do is up to here, we freeze it. We will not do any update. We will reuse it. The final few layers only, we will add a new layer and we train only those layers. That's called transfer learning. Okay. But this rule doesn't apply for every situation. So that's why we have some sort of illustrative guidance here. So in the vertical axis, we have the dataset size. So the bottom is small dataset, the top is larger dataset. And then there is a dataset similarity. Left is low similarity and the right is high similarity. Okay. Now in the bottom right, we have basically low small data set and we have big data set similarity. In that case, what you can do is you can frozen all of those initial layers and then fine tune only the final layers. But let's say you have a completely dissimilar domain and you also have sufficient data set, you have huge data set, probably it makes sense to train it from scratch. Okay. Then you will get better accuracy than this. It doesn't have to start training from scratch at the very beginning itself. You can try to do transfer learning and see, and then you can also experiment with training with scratch. Probably the training with scratch is more accurate than reusing some of those weights. Okay. Okay, so I think we covered everything that was planned for today. Any questions before we wrap up? It's been a long day. Thank you so much. See you next week. Yes, yes, yes. Abhi will upload it to the LMS platform.